Welcome to statics. This is a basic problem where our job is to draw the shear and moment diagram for this beam as it goes from A to B. And to get started on these problems, you always start by finding the external reactions. So I've already drawn a free body diagram over here on the right. The pin at A has the potential to cause a support force in the y direction and a support force in the x direction. There are no horizontal forces, and so therefore we can see that AX is 0. So we are left with basically finding the support at A and the support at B. These are purely vertical forces, and so as usual, we just simply we sum the forces in the y direction and set them equal to 0, and we see that AY plus BY minus 10 minus 40 is 0. We can also sum the moments at A. When we do that, we get that minus the 10 kilonewton force times 5 meters minus 40 times 10 meters plus By times 15 is 0. Solving for By, we find that By is equal to 450 over 15, which is equal to 30 kilonewtons. And because of that, we can plug that into there. If that's 30, then we conclude that AY is equal to 20. So this is our starting point. AY is 20 and BY is 30. And we are in units of kilonewtons and we are in meters. The distance between these, I should have labeled, is 5 meters. So as I said, step 1 is external reactions. And to do that, you have to have a free body diagram. You have to label what's going on, and then you have to kind of make sure everything makes sense. As a quick check, 30 plus 20 makes 50, 10 plus 40 makes 50. We do expect AY to be smaller than BY because there's more load on the right-hand side of the beam. So things look pretty good. So step 2 is to look at that load again and to divide the beam into regions that you will then analyze by cutting up the beam. So what I'm saying is that we are now going to think about this beam in segments. I'm going to call this segment 1, I'm going to call this segment 2, and I'm going to call this segment 3. And what I propose to do is we're going to take a cut through segment 1 at first. We're going to follow on by taking a cut through segment 2, and then the last thing we'll do is we'll take a cut through segment 3. So that's the plan. So here I am, I'm in segment 1, and I'm going to explain what segment 1 is. I am in the region between the origin and X and 5 meters. And so to be explicit, I should probably explain this is my origin, and X is going to be going on out in that direction. So if I take a look at my little region of the beam that I'm talking about that region of the beam right there, and to make it more clear, I'm going to draw it as a separate free body diagram. I know that AY is 20. I've cut it, all right? And so because I cut it, I have a possible shear force. I have a possible bending moment, or I'm going to call it moment at the cut, and I have a possible normal force. That's what happens when you cut up a beam, and that's what we're doing in these problems. We're trying to find the shear and moment forces as a function of distance. And so X, as I said before, is defined as this length along here. And so now the procedure is simply to apply the equations of equilibrium to this little segment. In other words, we're going to take the sum of the forces in the y direction, and we're going to set them equal to 0. Let me rewrite that. We're going to take the sum of the forces in the y direction and set them equal to 0. And when I do that, I see that 0 equals 20, and it's positive. I'm writing it as a positive number because it's pointing it up, minus shear. I write minus shear because the convention is on the left-hand face to draw shear as going down. And because it's pointing down, we simply write minus shear. Therefore, shear is equal to 20 kilonewtons in this segment, and it's a constant. Next, I'm going to sum the moments at the cut. To be explicit, this is where I am thinking about taking the moments. And so I have this unknown moment that I must write down. So the moment, the sum of the moments at the cut is equal to 0, which is equal to this bending moment that I'm trying to find. I draw it as positive because it has a counterclockwise rotation. The second thing that can cause a moment is this 20 kilonewton force, and it would cause a negative moment. So we write minus 20, and we have to multiply it by the distance. So what's the distance between the origin and that cut? Well, it's just x. So we put an x in here. And therefore, the moment equals 20x in this segment between 0 and 5. So, so let's do a quick check. dm dx should equal shear, right? And so we can take dm dx, and we see that we get a value of 20, and that matches what we found, and so things look pretty good. So we are now in a position to be able to plot these. So let's go ahead and take a look at the shear and moment diagram that I've kind of laid out here. And so what we've just found, if this is a value of 20, and this is kilonewtons, we have found that shear is a constant of 20 in this segment between 0 and 5. We've also found that the moment is 20 times x, and so when x is 0, moment will be 0. When x is 5, the moment will be 100. So let's let this value be 100 on our, and so what are the units of that? It would be kilonewton meters. And so we have a straight line, so that's what we have so far in region 1. So let's move on to region 2. So region 2 is where 5 is less than x, which is less than 10. So region 2 is right in there. So I'm going to draw a new free body diagram for region 2. So it looks like this. All right, so we have our AY value. AY was 20. We have our load at 5. So the load at 5 was 10 kilonewtons. So you have to draw on your loads. And then since we've cut the beam, we have an internal shear possible. We have a moment possible. And in this problem, there are no horizontal forces. So the normal forces across this whole problem are just 0. And I won't talk about them anymore. As before, well, I should probably write down what I'm doing. So now I'm in the region 5 is less than x, which is less than 10. This is region 2. So as before, we apply the equations of equilibrium. We write that the sum of the forces in this segment of beam is in equilibrium. So how can it be in equilibrium? Well, the sum of the forces in the y direction must be 0. So 0 equals, we have the load at A, which is 20. We have the, that's the reaction at A. We have minus 10, which is a load. And now we write minus shear. This is our unknown value that we're solving for. And therefore, we solve and we find that shear is equal to 10 kilonewtons across that whole segment. If we take a look at our diagram, what that means is that across this segment too, shear has dropped to 10. Now that's not a coincidence. It dropped to 10 because a load of 10 was applied right there. And so we observe that as we apply a load across the beam, we get a drop in the shear by a value of 10. So let's see what's going on with moment. Relative to moment, again, we are in equilibrium, so we write, and we're thinking about here, right? This is our mental position. And our objective is to find that M, which is the bending moment, present in that particular segment of the beam. So again, this beam is in equilibrium, so the sum of the moments at that cut point is going to equal 0, and that is going to equal this unknown moment that we're trying to find. And now we have to think about the moments caused by the 10 kilonewton force. So let's set up our number line here. So we have cut it at a value of x. This is a value of 5. It's a value of exactly 5 to that load right there. And so therefore this length right here will be x minus 5. That's the value of this length right there. So again, this 10 kilonewton force is x minus 5 away, and it will cause a positive moment about that point. So I add a positive 10 times x minus 5, and I move on to the load. Sorry, the reaction at A. This reaction at A will cause a negative moment. It is x away, and so I write minus 20 times x. Solving for M is therefore equal to 20x minus 10 times x minus 5. So let's ask ourselves, at x equals 5, what is M? Well, M will equal 20x. At x equals 5, which is equal to 100, which is good. That's what we had before when we were thinking about. This is the beginning point. It matches our ending point from the first segment. That's a good sign. So let's ask ourselves, at x equals 10, what is our moment? We will get a value of 150 at x equals 10. And so what we find is that the moment rises from 100 to 150 kilonewton meters as it proceeds along the beam. So we had this slope at first. The slope is decreased a little bit as we move to the next segment. So that is now the moment as we kind of have worked our way along this beam. So remember, we can check things. It should always be true within the segment that dm dx should equal the shear that we already found. So let's look at our equation for M. If we simplify that, that would be 10x plus 50. So dm dx will equal 10. That is what we had for shear, and so we're in good shape. Remember, they should always match. If they don't match, you have a mistake somewhere. Okay, so big picture now, we are ready for the third segment of the beam. That is to say, we're ready to think about what's happening between 10 meters and 15 meters on the beam. We are in region 3. So when I do this, I'm going to do this two ways, all right? I'm going to do this, I'm going to think about cutting the beam here and then drawing the left-hand side of the beam. That's what I'm going to do first. After I do that, I'm then going to show you that you get the same result as if you thought about the right-hand side of the beam. So let's do the hard way first. We're going to do the left-hand side of the beam. We're going to be between, we're in region 3. And I've cut up my beam. It's a pretty long beam. I have AY with a load of 20 at x equals 5. I have, so the 20 was the reaction. We have the load at 10. We have a second load of 40. So that's 5 and that's 10. And I've cut it at x. Okay, that's x is the dimension of my cut. Since I cut it, there are internal shear and bending moment forces possible. We already decided there were no normal forces. So what do? We write the equations of equilibrium. We sum the forces in the y direction, set them equal to 0. That is equal to positive 20 minus 10 minus 40 minus shear. Therefore, the shear is equal to 30 now. In order for this beam to be in equilibrium. Positive 20 minus 10 minus 40 minus shear. Shear must be minus 30 in order for this statement to be true. So let's look up at our diagram. Let's kind of keeping track of what's going on. What we have just concluded is that on the shear diagram, we went from 10 down to minus 30. This value is minus 30 on the shear diagram. And so does this make sense to us? Well, again, as I pointed out to you earlier, when you have a point load, you expect the shear to drop by the magnitude of that point load. And so what we have found on our shear diagram makes great sense. And notice that as we go on out to the very end of the beam, this minus 30, it's going to suddenly jump up at the very, very end of the beam back to 0 because it has a load of 30, it has a reaction of 30 at the end. And similarly, at the very beginning of the beam, it jumps up by 20, hangs out, comes down, over, comes down, over, and then up. So we understand shear. Shear looks pretty good. Again, keeping in mind that dm dx is equal to shear, this was a positive number. It was a positive number, and that was our slope. Our slope was 20. Our slope was 10, another positive number. Our slope decreased. And now that our slope is negative, we do predict a negative slope to happen. So we're not quite sure what, but I'd almost take a guess that shear is going to be coming back down to 0 because at the end of the beam there were no moments being applied. So that's my guess. Let's see if I'm right. So we're going back to thinking about region 3, and we are now summing the moments and checking for equilibrium. Well, we're setting equilibrium. So we're summing the moment again at the cut. We're thinking about what's happening here at the cut. So what's this distance? Well, if the total distance is x and this is 10, then this is x minus 10. This distance here is x minus 10. And this distance will be x minus 5. So the summing the moments at the cut, setting them equal to 0, we find that we write positive moment. That's what we're trying to find. Okay. We have a positive contribution from this 40 kilonewton force. We multiply it by x minus 10. We have a positive contribution from 10. We multiply it by x minus 5. We have a negative contribution of 20. Its distance from the cut is x, so we write minus 20x. That's all equal to 0. When we solve for moment, we find that moment is 20x minus 40 times x minus 10 minus 10 times x minus 5. If we simplify that, we find that moment is equal to minus 30x plus 450. Let's check dm dx. It better equal shear. Dm dx is minus 30, and that matches what we had found. So we are in good shape. Dm dx equals 30 equals shear. Things are matching and we're happy. Remember how we predicted it would be a negative slope? Yes, indeed, it was a negative slope. So now we just plug in a few values. At x equals 10, we should get 150, and we do. We get 150, which makes sense. When we plug in x equals 15, 15 times 30 is 450, and we get m equals 0. So let's go back to our diagram. This value is verified, this value is verified, and that completes the sketch of what the shear and moment diagram for the beam should look like. I want to do one more thing. I want you to think about the right-hand side of the beam up here, because it's an easier way to think about what's going on at this segment. In other words, if I think about the right-hand side of this beam, and let's highlight what I'm doing here. Let's go for orange. So if I think about this segment of the beam right there, what's going on with it? Well, it is being supported by By with a value of 30 kilonewtons. Okay, it also is going to have internal forces. When you think about so this is where I've cut it. This is the end of the beam, and I am x away from it, right? That's x, and this total distance is 15. So this length is 15 minus x. When I cut a beam and I draw the internal shear and moment values, you must reverse the direction. So shear on the right-hand side must point up. I want to repeat that. Shear on the right-hand side of the beam must point up. The reason for that is that it pointed down on the left-hand side of the beam. And these are internal forces, so they must cancel out. By convention, the left-hand side of the beam is down, has a positive shear pointing down, and the right-hand side has a positive shear pointing up. Similarly, what's going on the left-hand side of the beam must be counteracted at the right-hand side of the beam. So I write positive moment like that on the right-hand side of the beam. So let's consider the equations of equilibrium, and let's sum the forces in the y direction on this right-hand side of the beam, and we should get the same answer. So in this case, positive shear is pointing up. So I write down shear, positive shear, just like that. And I add in the other thing that's happening in the vertical direction, which is 30. And then when I solve for V, so that is equal to 0. When I solve for V, which is the symbol for shear, I get that shear is equal to minus 30 kilonewtons. Well, that's good. That's what we were hoping we would get. That's what we had before. This will be true if you've correctly been managing these directions of shear on the left and right-hand side of the beams. Similarly, when we sum the moments at the cut, and this time we're summing the moment right here at the cut here, I have to put the bending moment here, which I'm trying to find, and we write it as minus m because it's going clockwise. So we write down minus m, and then we think about what this 30 kilonewton force will do, and that 30 kilonewton force would cause a positive moment at the cut. And so I would write 30 kilonewtons, and its distance away from the cut is 15 minus x. So I write plus 30 times 15 minus x. And therefore, this bending moment at this particular location on the beam, where 10 is less than x is less than 15, is equal to 30 times 15 minus x, which is what we had before. So the moments match, everything is good, and you should now feel pretty comfortable about breaking up the beams into pieces, solving the external reactions, that's the next step. Then you break the beam up into pieces, you carefully write the equations of equilibrium, you go on to the next segment, you write the equations of equilibrium, you check that dm dx equals shear, and remember, you can think about the left-hand side of the beam or the right-hand side of the beam. All right, so that concludes this somewhat simple problem. I'm going to post a second problem that adds a distributed load, but make sure you understand how to do this before trying the more complicated problem.